Hi, AP Physics students. Another Chapter 6 problem that I've had a couple of questions about is number 51. And this is a problem about power, which we only just touched on in the video lecture, the last video lecture. So it's not surprising that you're having questions here. So let's review again what power means. So power is the rate at which energy changes. That's just the broad definition of power. Our units are joules per second, energy per time, and that's equivalent to a watt. So the watt or joule per second is the SI unit of power, but the British, oh, whoops, there's a T in there, and an extra I. British unit is horsepower, right? And that's what we sort of are interested in if we're talking about cars or something. So power is the rate at which the rate at which energy is changing, but we know that work is a way to cause changes in energy. We know that if I push something and move it, I'm doing something to change its energy, either lifting it or sliding it, changing its gravitational potential energy or changing its kinetic energy, or causing kinetic energy or work to be transformed into heat through friction. So this idea here leads us to a sort of alternate definition for power, and that is that power is the rate at which work is done. And in terms of motors, that's more appropriate because motors do mechanical work, like that's the point of a motor. So work, we also understand, is force times displacement. Force times displacement is our definition for work. This is, of course, force times displacement times cosine of the angle between the two. But if we assume that the force is in line with the displacement, we can kind of drop that cosine of theta. So I recognize that distance per time has another physical meaning, particularly in kinematics. Distance per time is velocity, right? Or at least its average velocity. So if force is constant and if velocity is constant, we can simplify power or rewrite power as force times velocity times cosine of the angle between them if they're not parallel to each other. All right, so this leads us to problem 51. So in fact, let me see if I can just sort of slide this up because we want this equation for 51. Let's see if I have enough room on my desk to do this. Yeah. All right, so problem 51 says a car generates 18 horsepower when traveling, or horsepower, when traveling at a steady 95 kilometers per hour. So there we have that sort of velocity is constant. So I've got power equals 18 horsepower. I have velocity is constant, 95 kilometers per hour. What must be the average force exerted on the car due to friction and air resistance? Well, I know that the engine is essentially thrusting the car forward, right? The forces on the car, normal force, pull of gravity, thrust of the engine, which is more complicated than just a push forward, but it essentially the net force of the engine is forward, net force of the engine and the tires and the friction on the road. But that's more complicated than we need it to be. We can model it as a sort of jet engine thrust forward. Then there's air resistance. Oh boy, spelling air resistance. Resistance. It's futile. Air resistance and internal friction and all of that other stuff, right? All those dissipative, conservative forces. So we have a forward push and a backwards, like resistive force. And if it's traveling at constant velocity, those forces, forward and backward, must be in balance. So it's asking us what the average force exerted on the car due to friction and air resistance is, but I'm thinking about this in terms of the power expended by the engine. A car generates 18 horsepower, the engine generates 18 horsepower, has to do with the sort of thrust force, the net thrust that the engine produces, times the velocity of the car times cosine of the angle between the two. So the car is moving to the right. D is to the right. So theta is 0. So cosine of theta is 1. And so we drop that term. So I've got a power of 18 horsepower. I've got a velocity of 95 kilometers per hour. And I want the force, the engine push, right? So now I have a little issue of units, right? Because this all works out to watts, newtons, and meters per second, but none of this is in the right units. So let's see, I Googled it, and 1 HP is equal to 745.6. Where did it go? 745.7 watts. So let's round it up to 746 watts. So that'll get us into watts, right? Get rid of the HPs. And then kilometers per hour, we go 1,000 meters per kilometer. And we go 3,600 seconds per hour. And now we're in meters per second. So we've got 18 times 746. 13428 watts, and 95 by 1,000 divided by 3,600, so 26.39 meters per second. And now finally I put it all together in my rearranged power equation, where I have 13,428 watts equal to the velocity of 26.39 meters per second times the force pushing it forward by the engine. So the force turns out to be 508.9. Let's just have 3 digits. 509 newtons. Did I tell you in class, I think that 3-digit rule of rounding came from slide rules. I'll have to talk to my dad over Christmas break, but I may have a fun fact for you after the break. I hope you're having a nice Christmas break or holiday, a nice winter holiday. Please email me if you have any additional questions. I'll have my laptop with me, and maybe I'll take my little camera home and I can answer questions by video or by email if you have any.